Hello, it's Jonathan Templin, and I'm back with another lecture. This is Multivariate Models, Robust Maximum Likelihood, and Relative Model Fit for EPSY 905, Fundamentals of Multivariate Modeling. This is online lecture 12. In this lecture, I'm going to talk about the version of maximum likelihood used in Lavon to estimate multivariate linear models, and how that works with the scaled likelihood ratio tests, and how R does this all for you automatically. The example dataset, again, is the example that I've used in the introduction to multivariate linear models and the absolute model fit test. It's data I simulated from a study in 1994 involving self-efficacy and self-concept beliefs in mathematical problem solving. There were 350 people in this study. About 10% of the data are missing. Here are the variables, once again, in the study. One I'll be using today, the two, I'll be using in this lecture is perceived usefulness of mathematics, and the second is mathematics performance, or performance on an 18-item multiple choice math test. The model we're going to start with today is a multivariate model, empty model, looking at predicting performance and usefulness simultaneously, where both of those single model equations have an intercept, and both have an error term that has a residual variance, so residual variance for performance, residual variance for usefulness, and then there is a covariance as well. Now, Model 2, this is from the Introduction to Multivariate Models lecture, estimated this covariance in the off-diagonal, whereas Model 3, we set it to 0. And we're going to compare these two models based on their relative fit. So, we're going to start, though, with robust maximum likelihood, which is an estimation method that really is exclusive to path analysis modeling software right now, although it doesn't have to be in theory. So, robust estimation of maximum likelihood still assumes the data follow a multivariate normal distribution. But the key is the way that where robust, or the term robust, comes into play. A robust statistic, by the way, is one that is somewhat what am I trying to say here? Somewhat resistant to to violations of assumptions. So if you can think of just your classical statistics, take the mean, for instance. The mean is highly impacted by the presence of outliers, right? If you have one data point that's way outside of the central part of a distribution, the mean will get pulled up by that data point. But a more robust version of the measure of central tendency instead of the mean might be the median, because one data point will not skew the median. It's just one more percentage point above the median. So, like that, robust maximum likelihood exists as a more robust form of maximum likelihood in that it is more robust to data that has kurtosis values that are different from a normal distribution. Now, what is kurtosis? And can you cure it with penicillin? I don't know. Kurtosis is a measure of the shape of a distribution. Really, it comes from the Greek word for bulging. Don't get me wrong, I had to look that up. But we can estimate a data set's amount of kurtosis, or in a multivariate sense. And the degree of kurtosis in a data set is related to how incorrect the log likelihood value might be. If you have something called leptokurtic data, that is where your tails of a distribution are too heavy, it's too inflated, the chi-square gets inflated and your standard errors likewise become too small, the standard errors for each of the parameters. Alternatively, if you have platykurtic data, right, this is where you have too thin tails, the chi-square is depressed and the standard errors become too large. So the goal of a robust maximum likelihood estimator is to correct an analysis statistics based on its estimate of how kurtotic, if that is a word, your data happen to be. So here's an example of kurtosis from my favorite, Wikipedia. The black line would be a normal distribution with zero kurtosis, but you can see all the other values of kurtosis for different distributions as you go along, or different shapes, and how they vary. All right, so more leptokurtic distributions are more peaked here. Platykurtic would be flatter as you go along. So to get robust maximum likelihood to be invoked in Lavon, we just need to add this estimator equals MLR right to our the end of our as an argument in what we do. Now, because of the way it works, if you might recall from our initial introductory multivariate model, linear models lecture, I said we're just always going to put it on as a part of the estimator. And that's because if our data are truly multivariate normal, meaning they're no longer, they're not platykurtic or leptokurtic, then the result we will get is exactly what we would have if we had multivariate normal data. So it's nice. But if our data aren't exactly like multivariate normal, then the robust maximum likelihood is going to help adjust it. So what it's going to do is it's going to give us a scaled or a different chi-square value, and everything that goes with that chi-square value gets adjusted as well. That means model fit statistics, the RMSEA, the CFI, and the TLI. Furthermore, it will also adjust the standard errors of all of our parameters using something called the sandwich estimator, which seriously does exist. I'll just leave it there. There's lots of bad jokes you could have with that one. So what happens if you have, when you go and estimate a model, you'll find that, here, let's go back to our R syntax that we have here. This is the R syntax for this this lecture. I read in our data, and we go down to model 2. This is the model with the covariance estimated, and take the summary statistic. Now when you go and look at, actually let's go to model 3 because this doesn't show it. Go down to model 3 here, and look at the summary from model 3. You can see, first of all, there is a robust column that shows up in the output, and that's because we use robust maximum likelihood. But down with the log likelihood for the model that you'll see, and the saturated model that's estimating, it also estimates a value for the scaling correction factor. And that's that value that helps adjust the log likelihood, making it either too big or too small. If that scaling factor is equal to 1, then it's perfectly multivariate normal data when it comes to kurtosis. There's zero kurtosis. If it's bigger than 1, the tails are a little bit too fat or leptokurtic. If it's less than 1, the tail's a little bit too thin, and it is platykurtic. So now the scaling factor will show up on all your likelihood ratio tests. But R will do this for us, hooray. Whereas M+, when it first came out with this, and I think it's still like that, will not. So things will be fixed. So now let's take a look. We have ML and we have MLR. We estimated the saturated model and the independence model. It's model 2 and model 3. And let's compare those results here in the slides. Here are the model 3 results. You can see the values for the likelihood ratio. The log likelihood. Let's go down to log likelihoods first. You see the log likelihood under ML and robust ML is the same. The only difference is there's a scaling factor that shows up in robust ML. That scaling factor gets combined using a formula I'm about to show you in 2 slides to give us this overall scale correction factor that goes and gives us this chi-square statistic. So similarly, we can find the same thing when it comes to model 2. And our new likelihood ratio statistic is -2 times the difference in log likelihoods divided by the scaling factor. So if we go back here, our chi-square that came from our likelihood ratio test comparing a maximum likelihood model 2 and model 3 was 5.573, which really is 6.064 divided by 1.088. That's the scaling correction factor. If you want to compute it by hand, there you have it. Here's how you can actually do that. It's not really that exciting to compute by hand, so I just usually leave that to R, and it does a pretty good job in that regard. And so you can see the same thing happens if we were to compare models using the ANOVA function. It would also give us a scaled chi-square. You can see that with the Satora-Bentler 2001 in parentheses here describing that. And here you can take a look at the model results. What happens to our standard errors? You'll see that they're mostly the same between these two data sets, and that's because this is simulated data, and it behaves pretty much the same way for either. But take a look at what happens. You start to see the standard errors adjusted a little bit under the ML and MLR, in that the standard error for the variance goes up for MLR and down for performance, but down from ML for usefulness. So it adjusts things a little bit slightly, depending on the test itself. So the take-home point here is use the MLR whenever you're using maximum likelihood in linear mixed models. But that said, the MLR does not protect you from data that don't exactly meet the other assumptions of multivariate normality. In particular, if you're using Likert items, if you're providing a scale that has people respond with 5 categories, you can still use MLR for those, but those categories are not continuous, and that's what's going to cause an issue with the estimation, and MLR will not fix that. So that is a nice thing. So in wrapping up, model comparison, really this is more about maximum likelihood, robust maximum likelihood. We'll use it for every one of the models that we put in our class when it comes to path analysis. So that's all for now. Thank you for watching.